So good afternoon everyone. So today is the second lecture of this week 2. So today we will cover the basic concepts of digital communication systems like bit error rate of different modulation schemes, and we will see about the additive white Gaussian noise. So we will cover the basic concepts so that in upcoming lectures it will be very useful, and also if any like problem in the first or second week, that can be covered easily with this concept. So we'll cover most of the theoretical concept today, and we will solve few examples in between or at the end. So we'll start the lecture now. So first we will look at the Gaussian random variable, because most of the things we are dealing in this lecture series are like noise and all are Gaussian.
Excuse me, sir. Good evening. I want to know one facts about these concepts. Please tell me, sir.
A Gaussian random variable uh, is represented as, let's suppose we say it have a mean mu and variance sigma squared. So this can be represented as this notation. The first part is the mean and the second part is the variance, and the probability density of this Gaussian random variable is given as 1 by root 2 pi variance into e to the power of minus x minus mean, x minus mean square divided by 2 into variance. So this is the probability density of Gaussian random variable. This Gaussian random variable is even function, like it is symmetric with respect to the y-axis, and also like when we keep the mean 0 and variance, let's suppose mean is equal to 0 and variance is equal to 1. So this is known as the standard Gaussian random variable. Mostly we will use this in this lecture series. So now the probability density function will become 1 by square root of 2 pi e to the power of minus x squared by 2 of sigma square. And this is also a function denoted by qt, which is used to find the bit error rate. So this is known as q function. So basically qt is probability of q such that the variable x is greater than equal to t. So Let's suppose this is our standard Gaussian random variable whose mean is at 0. So the peak value occurs at mean. So now here the probability such that x is greater than t. Let's suppose this value is t. So this is our q of t. So q of t is denoted as integration from t to infinite 1 by square root of 2 pi e to the power of minus x squared by 2 dx. So up to this clear. So now we will see, like let's suppose there are an independent zero mean Gaussian random variable that is like x1 to xn, and each one is having different variance sigma I square. So we will see like what will be the linear combination of above random variable as. So this is one of the useful property of Gaussian random variable. Like let's suppose x1, x2 up to xn are n independent zero mean Gaussian random variable. Now each random variable xi can be represented as a standard Gaussian random variable, that is mean 0 and variance sigma I of square. So now if mean is 0, so expectation of xi and xj. So xi and xj are independent. So we know that for independent variable, this we can write as the product of both the like expectation of the product of both the functions. So let's suppose two functions are independent, then their expectation, like expectation of multiplication of both the function, will be expectation of the multiplication of individual function. So this we know. So now we know that each value is equal to 0, because from here we can derive e of x1 is equal to e of x2 dot dot equal to e of x1 xn is equal to 0. And now, so this will only valid when I is not equal to j, because when I is equal to j, then e of xi will be e of xi square. So let's suppose a function y that is the linear combination of above random variable. So y is the linear combination of above random variable. Now a1 a2 are just a coefficient of the combination, and the random variable y follows a Gaussian distribution with mean. So the mean of y, now let's find the mean of y. So that is equal to expectation of y So this will become expectation of, we can write y as summation of ai xi, and I is equal to 1 to n. So this will be expectation of summation of ai xi, I is equal to 1 to n. So this will be equal to summation of ai will come out because ai is the constant term, and expectation of xi. Now we all know that expectation of xi will be 0. So the mean of y will be 0. Now we will see the variance of y. Y is actually the linear combination of above Gaussian random variable. Now we will find expectation of y square. So for this, this will become expectation of sigma ai xi, I is equal to 1 to n square. So this will become expectation of sigma ai xi aj xj. So this we can simply write summation of I is equal to 1 to n, j is equal to 1 to n, ai aj xi xj. So whenever, like we have already seen here, whenever I is not equal to 0, e of xi xj is equal to 0. So for only, so we can simplify this as I is equal to 1 to n, j is equal to 1 to n, ai aj xi xj. Only we have to find when I is equal to j. So this we can now simplify. I is equal to j, so it will become ai square and xi square. So now expectation of xi square will be sigma I square. So this will be ai square is constant, so it will come out, and this will be sigma I square, and summation will be I is equal to 1 to n. So y is also a Gaussian random variable with expectation of y is equal to 0 and variance of y variance can be given as y minus mean whole square. So now mean is 0, so like Sorry, in between my internet is gone now. Okay, due to the power cut, so I have connected with my mobile phone. So now y bar is 0 because mean is 0 as we have calculated above. So this variance will be simply E of y square. And now E of y square, what we have found is this. So this is equal to summation of ai squared sigma I squared. So now y is also a Gaussian random variable, but it was the linear combination. So this is the important property of Gaussian random variable, that their linear combination is also a Gaussian random variable. So we can write this as a note. Linear combination of Gaussian random variable is also Gaussian. So for a summary till now, like we had an independent Gaussian random variable x1 x2 dot xn. Anyone wants to join this call? So x1 to xn is the n Gaussian random variable. So their linear combination y a1 x1 plus a2 x2 plus an xn is also Gaussian random variable, and it can be denoted as mean is equal to 0 and variance is summation of ai squared sigma I squared. So this property we will use throughout the lecture. Now we will see bit error rate performance of various modulation scheme in this digital communication system. BR of and we'll solve some of the question based on this. And also this video is recorded, so it will be uploaded in the YouTube and the link will be shared through the NPTEL portal. So now we will see bit error rate performance of the communication system in additive white Gaussian noise. So first we will take bit error rate of BPSK system. Let's suppose the symbol 0 represented as minus of root p and symbol 1 represented as root p. So this is the BPSK symbols. So here the transmission of BPSK symbols plus root P and minus root P to denote the information bit 1 and 0 respectively. The system model is described as given. Yk is the received signal, that is equal to xk transmitted signal plus nk noise signal. So this is received signal, this is transmitted signal, and nk is the noise. So due to noise there is some error occurred, so we have to find what will be the bit error rate due to the noise. So let's suppose after receiving we have to make a decision whether the transmitted signal was 0 or 1. So after receiving, the decision made was xdk, this will be 1 if yk is greater than 0 and 0 when yk is less than 0. Now let's suppose xk is equal to 1 and xdk is equal to 0. This means transmitted 1 received is equal to 0. So therefore error occurred. Similarly, xk is equal to 0. Let's suppose transmitted is 0 and the decision made was 1, like the received signal was 1. Received is 1. So error has occurred. So error occurred when and xk is not equal to x of dk. Okay. So in this case, so in what case, like yk is given as xk plus nk. Now let's suppose xk is minus root p. This means bit 0 is transmitted. Now if xdk is equal to 1, that is root p, so that is greater than 0. So this means yk will be greater than 0. So minus of root p plus nk is greater than 0. So nk is greater than square root of p. So if the noise power is greater than the square root of p, then the bit error rate has occurred. So now what will be the power like probability such that nk is greater than root p? So this will be, as the noise is Gaussian random variable, so this will be the probability density function we have already seen for this noise is here, as we have seen. So we will use the same equation. This is the probability density function, so the integration will be the probability value. So this will be square root of p to infinite e to the power of minus t square by 2 sigma square dt. Okay, so now let's suppose t by sigma is equal to u, then dt is equal to sigma du. So the probability such that noise power is greater than root square of p, that is equal to 1 by 2 pi, this will be in square root, sorry, and when t was root p, then mu will be t by sigma, so that will be root under p by sigma square, because when you bring sigma into a square root it will become sigma square to infinite, because when t was infinite mu will be also in, u will be also infinite, e to the power of minus t by sigma is u, so it will be u square by 2 and sigma du. So this sigma and this sigma square will get cancelled, so finally we will get square root of 1 by 2p integration from p by sigma square to infinite e to the power of minus u square by 2 du. So this is a q function, and q function of what? The value which is the lower integral. Okay, so this will be q function of square root of p by sigma square, and this is also the p by sigma square is the signal power divided by noise power, so this will be a square root of SNR. Here SNR is equal to p by sigma square, and also sometime SNR is given in dB, so when it is in dB we have to convert into the normal value, so SNR in dB is equal to 10 log 10 p by sigma square. And one more assumption we can take, or approximation we can say, what we have studied in last lecture also, but today we will see for M array PSK, and also for PAM signal, and also for M array PAM signal, the bit error rate for all this digital communication scheme. So now, like q of square root of SNR, like as we know that q of x is less than equal to half e to the power of minus x square by 2. So this can be approximated as half e to the power of minus x square by 2. So according to this approximation, we can write that is approximated as half e to the power of minus x square. So here x is square root of SNR. So minus of square root of SNR square will be minus of SNR by 2. So it was very simple. So we'll solve a simple question. After that, we will go for bit error rate of quadrature phase shift key. And also the constellation diagram for BPSK is given as this. This is square root of p, this is square root of minus p. Now coming to a question. We have to find the bit error rate of binary phase shift keying communication over an AWGN communication channel at SNR is equal to 10 dB. So we all know that bit error rate is Q function of square root of SNR. But here we have to find the actual value of SNR. So SNR in dB is given as 10 dB. So 10 log 10 of SNR is equal to 10. So SNR will be also 10 to the power of 1. So this is equal to 10. So bit error rate is equal to Q function of square root of 10. So when we find this Q function of square root of 10, this value 7.82 into 10 to the power of minus 4. So in this way we can solve easily these questions. If you have any doubt, you can ask. Now we'll solve one more question. Compute the SNR dB required for probability of bit error rate 10 to the power of minus 6 over an AWGN channel. So in this, a bit error rate is given, that is 10 to the power of minus 6. Now we have to find the SNR, and that too in dB. So we all know that Q function of a square root of SNR is equal to bit error rate. So that is given as 10 to the power of minus 6. So Q inverse of 10 to the power of minus 6 is equal to a square root of SNR. Now Q inverse of 10 to the power of minus 6 square will be SNR. So the Q inverse of 10 to the power minus 6 is 4.75. So this value you can find from the Q table, which is available. Q chart is available on internet. So SNR is equal to 4.75 square, or mostly this will be given in the question as well. So this will be 22.60. Now SNR in dB is equal to 10 log 10 of SNR. So that is equal to 10 log 10 of 22.60. So this is equal to 13.6 dB. So we have solved this question. Now next concept we will see, that is the bit error rate for quadrature phase shift keying in additive white Gaussian noise. So next topic is bit error rate and symbol error rate. Now what is the symbol error rate? Like we have only studied bit error rate in the previous modulation scheme, that was binary phase shift keying. Why we are studying SER for QPSK, why not for BPSK? Because in BPSK transmitted bit was only 0 or 1. 0 or 1. So, and this is also the symbol 1, and this is symbol 2. So that's why their bit error rate is equal to SER, because both are same in BPSK. Now coming to QPSK, it can be transmitted symbol R. Here we can write transmitted symbol 00, 01, 10, and 11. So, so there can be error in bits. If error in bits is there, then definitely there is the error in the symbol. Okay, like let's suppose this 00, like transmitted was 00, received was 11. There is error in this bit also, error in this bit also, but number of symbol error is only one, because there is a one symbol only transmitted. So here this is the difference between symbol error rate and bit error rate. So this is required in QPSK but not in BPSK. So now we will see how to find the constellation diagram of QPSK is given as in QPSK there is a complex constellation diagram. What does this mean, complex constellation diagram? Like each symbol is phase shifted by 90 degree. That's why it is quadrature phase shift keying. Earlier the phase shift was 180 degree. That was, it was a binary phase shift keying. So let's suppose this is symbol 1, that is a square root of p. This is our imaginary axis and this is our real axis. So this point is square root of p by 2 and this is also a square root of p by 2. And this is minus of square root of p by 2. Similarly here minus of square root of p by 2. The second symbol will come here and the third symbol will come here and the fourth symbol will come here. So I will represent symbol with different color. First symbol, second symbol, third symbol, fourth symbol. And each symbols are phase shifted by 90 degree. So the symbol given as plus minus square root of p by 2 plus minus square j into square root of p by 2. Okay. Now total power of symbol 1, that is square root of, let's suppose, p by 2 plus j of square root of p by 2 is equal to a square plus b square. Generally this is the power, so this will be p by 2 plus p by 2, that is equal to p, so which is constant. And also that was same in the BPSK also, because it was square root of p and square root of minus p. So the total power of each symbol is P. And now the noise also is given is like complex constellation noise. So we consider noise to be complex Gaussian in nature. So for QPSK, we consider NK noise as a NIK plus J of NQK. What is NI and NQ? NI is the in phase and NQ is the quadrature phase Gaussian noise components. Okay. NIK comma NQK denotes in phase and quadrature Gaussian noise. So expectation of this like the noise signal we have to find. So this is the total power. Like we have to find the signal is to noise power ratio. So we will find the total power of the noise. So that is expectation of NK square. So the power of in phase is equal to sigma square by 2, and power of quadrature phase is also sigma square by 2. So the power of this noise is equal to sigma square. Now what will be the like signal power to the noise power? So that will basically be P by sigma square, because total power is P and also the noise power is sigma square. So SNR is again in this case will be P by sigma square. And bit error rate, I will write with other color. Bit error rate will be same of each channel of QPSK is identical to BPSK. So bit error rate of QPSK is given as same of BPSK, but there will be symbol error rate here. Symbol error rate means like sometimes there will be 2 bits in error, but there will be only one symbol error, because one symbol consists of 2 bits in the QPSK. So now P of E is given as probability of error in bit. So the probability of each bit is received correctly is 1 minus P. Okay. Therefore, probability that both the symbols are received without error is 1 minus PE square. Both the symbols here means quadrature phase and in phase. without error is equal to, like this is for the first symbol, for the second symbol 1 minus PE. So this will be 1 minus PE of whole square. So now we have to find the probability of symbol error rate. So probability of symbol error rate is equal to probability that, like it will be probability that one or both bits are in the error. Let's suppose transmitted is equal to 0 0. So when receive is 0 1 1 0, yeah, 1 1. In all the case there is a symbol error rate. So that is equal to probability that one or both bits are received incorrectly. So in this case, that is equal to 1 minus P square. So this will be 1 minus 1 minus P square plus 2 PE. So this is equal to 2 PE minus PE square. So probability of error is very less. So PE square is much lesser than PE. So here we can say that probability of symbol error rate is approximately equal to 2 of probability of bit error rate. So the net symbol error rate is twice the bit error rate. We can conclude the note point. Net symbol error rate is of QPSK is approximately twice the bit error rate. So till now, any doubt? Like in this way we can find. And we have also seen the constellation diagram. So this is our constellation diagram. So now we have done for BPSK, QPSK. So now we will see the bit error rate of M array pan. So what is M array pan? Like the first we will see the constellation diagram. With that we can understand it easily. So the constellation diagram, like each symbol will be separated by 2 delta. The last will be 2m minus 1 delta. Like there will be M array pan means there will be M symbols. Okay. So this one will be delta, 2 delta, 4 delta, 2m minus 1 delta, and here it will be minus delta, minus 3 delta. Sorry, here also it will be 3 delta because it is separated by 2 delta. Minus 5 delta and so on. The last will be minus of 2m minus 1 delta. So we can represent each symbol as plus minus 2i plus 1 delta. Okay. where I is from 0 to m minus 1. The constellation is shown as drawn in the above picture, and the quantity m can also be related to the number of bits per symbol. So b is number of bits per symbol. So this b is given as log of 2 into 2m. So what will be the value of m? M is equal to 2 to the power of b minus 1. So for example, let's suppose b is equal to 3, which corresponds to 8 PAM, that is 3 bits per symbol. The amplitude levels, like here you can see, let's suppose b is equal to 3, then here m is equal to 2 to the power 2, that is equal to 4. So now how many symbol will be there? That is plus minus 2i plus 1 delta. Okay, and I is greater than equal to 0 and less than equal to m minus 1. So value of I is less than equal to 3. So I will be 0, 1, 2, 3. So what will be the symbols here? SI will be, when I is equal to 0, it will be plus minus delta. For I is equal to 1, it will be plus minus 3 delta. For I is equal to 2, it will be plus minus 5 delta. For I is equal to 3, it will be plus minus 7 delta. So the constellation diagram will be like this. So this is for 8 array PAM. Okay. Here for the confusion, like here this m and this m is different, so better we will take here n. Okay, so it won't give you the confusion, because here we are finding m is equal to 4 and at down we are finding m is equal to 8. So let's assume this value as variable as n. Okay, so now we have to find the average symbol power p of this constellation diagram. Because when how do we find the bit error rate? Q function of SNR. So SNR is equal to noise, signal power by noise power. So we also have to find the average power of this M array PAM. So of the given constellation. So power is equal to, average power means 1 by M summation of k is equal to 0 to m minus 1 2k plus 1 delta square. Because each symbol is represented as 2i plus 1 delta, so we have taken instead of I k here, so 2k plus 1 delta square, and we will divide by m. So because let's suppose there is total number of symbol is m, so power is equal to, this delta square will come outside, we can write 2k plus 1 squared as 4k squared plus 1 plus 4k. Now the summation will be summation of this 4k square term. This can be written as 1 plus summation of k is equal to 0 to m minus 1 4k plus summation of k is equal to 0 to m minus 1 4k square. So this first term will give as 0 plus like m minus 1 time 1. So this is equal to m. So this will be 1 plus 1 plus 1 plus up to m time. So this term will become m. We know the summation of this as this 4 will come outside. Summation of constant k will be m into m minus 1 by 2. Summation of n integer is n plus m into m minus 1 by 2. Similarly, the summation of k squared like n number starting from 0 to m minus 1 will be m into m minus 1 into 2m minus 1 by 6. So these are the basic formula, summation formula. So we can write now p is equal to delta square by m, or we can cancel this m here directly, because in every term there is one m value. This will become now 2m minus 2 plus minus 2m minus m, that is minus 3m plus 1 by 6. 12m minus 6 plus 2m square minus 3m plus 1 by 6. So this is equal to delta square 2m square plus 9m minus 5 by 6. Am I doing any miscalculation somewhere? Two m square minus 2m minus m minus 3m plus 1 minus 6 12m. So basically when we do correctly it will become 4m square minus 1. So I must have done some miscalculation. So we can calculate it again, or we can directly write what will be the final equation. So the final power, when you calculate this value, we will get del square by 3 4m square minus 1. So now what is the value of m here? Like here we have written 2 to the power of b minus 1. So p is equal to del square by 3 4 2 to the power of b minus 1 into 2 minus 1. So p is equal to del square by 3 so the power of this M array PAM is delta square by 3 into 2 to the power of 2b minus 1. Now in the constellation diagram we can see like there are two kind of symbols, one the intermediate symbol and one the edge symbol. So these are the edge symbol. Why we are considering this? Because intermediate symbol can have interference on both the side, but edge symbol have interference only on the, like this have only on the negative like left side, and this have only the interference with the right side symbol. So intermediate symbol. So let's suppose, so these are total m minus 1, m minus 2 intermediate symbol, and total edge symbol are 2. Okay. So the here the noise, like we'll write here, for m minus 2 intermediate symbol, the noise variance is greater than delta or minus delta, sorry, or less than minus delta, then error occur. Here you can see, like for intermediate symbol, if it is like there is some symbol here at, let's suppose, 2 delta. So if you add something which is greater than delta, then also it will go this side. If you subtract also something which is greater than minus delta, this will come this side. Okay, let's suppose symbol is here 2.5 delta. If you add delta, it will go this side. So error occur by addition or subtraction of delta. Okay, like if the noise power is greater than delta or less than minus delta, then error can occur. So probability of error is equal to the noise power is greater than equal to delta, or the noise power is less than minus delta. So we can write like this by dividing it by sigma. So this will become the total probability error is basically become like both the value have the same answer, like both the, like this have some integration, like we can do q of x1 q of x2. So both are symmetric towards the y-axis, so both will have the equal value. Okay, so that we can write 2 into q function of delta by sigma, because this we can write it as q of delta by sigma. Okay, so this is our bit error rate for n minus 2 intermediate signal. Now and probability of, like this is for intermediate, we will denote it as intermediate. Probability of error for the edge symbol intermediate symbol This is probability of error for edge symbol. So this will be simply Q of delta by sigma, because the probability occurs when the noise is either greater than delta, or for the left edge it will be either less than minus delta. Okay, so now the average probability of error is equal to 2m minus 2. Total number of symbol is 2m minus 2 for the edge one, for the intermediate one, into 2 of Q of delta by sigma plus 2 by, there are two edge symbols, so that is 2 by 2m. We are calculating the average value into Q of delta by sigma. So this will be equal to, now both the term have Q of delta by sigma term common, so we can take this as common. So this will become 2 of m minus 1 by m plus 1 by m Q of delta by sigma. So this can be written as 1 minus 1 by 2m. So this is the probability of error for the M array PAM signal. And now what is the value of delta? Delta we have calculated here. P is equal to delta square by 3, 2 to the power 2b minus 1. So delta is equal to, like, P was equal to delta square by 3, 2 to the power of 2b minus 1, that is the power of the symbol. So delta is equal to, delta square is equal to 3p by 2 to the power of 2b minus 1, and when you do the square root we will get this value of delta. So the final average of M array PAM symbol is equal to 2 into 1 minus 1 by 2m. Q function of delta value is 3p by 2 to the power of 2b minus 1 sigma square. Now coming to the symbol error rate. So again we will find the symbol error rate as symbol error rate of M QAM. Now this was the PAM, so what will be the QAM here? QAM will be just like how it was the QPSK, but it will be extended of PAM. It will be extended in all the direction. So dot 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 dot. So this is a constellation diagram of M array QAM. So the probability of error of QAM is equal to 1 minus probability of error of PAM square. How we have found in that the probability of error of QPSK from BPSK, same thing we will apply here. So this will become 2 of P of PAM minus P square of PAM. So that we can approximate as 2 into probability of error of PAM. So simply we can multiply it by 2 and we can find the symbol error rate of M array QAM. Now the last one we will find bit error rate of MPSK. What is MPSK? Like QPSK we know there will be 4 symbol, BPSK we know there will be 2 symbol. MPSK means, let's suppose this is circle, so there will be M symbol here. Symbol 1, symbol 2, symbol 3, symbol 4, like dot, total will be M symbols. Okay, so the angle between each symbol will be here. Like this circle is not correct, so let me make it again. So the angle between, total angle is 2 pi and there is M symbol, so this angle will be 2 pi by M. Okay, so this distance, how much it will be? Let's suppose this is our 90-degree and this is square root of P. So sine of 2 pi by M is equal to, let's suppose this is D. So sine of, we'll break this into a smaller part because now break into more smaller parts so that this approximation will be correct. And now this will be perfect, like more near to the 90-degree angle. And this value will be pi by M and this is D. Okay. So sine pi by M is equal to perpendicular by hypotenuse, so P by root under of D. So D is equal to, sorry, root under P. Root under P of sine of pi by M. Now this complete value, okay, this complete value will be 2 into D. 2 into root P of sine of pi by M. So this is like distance between two symbols in MPSK. Okay. So the probability of error will be probability from, let's suppose this is our zeroth symbol, 0 to 1. Like if due to noise it is received the first symbol, or probability due to 0 to M minus 1. Like let's suppose this is our M minus 1 symbol. So if this value go this side or this side, so there will be error. So the total error will be 2 of q of a square root of 2 into SNR sine of pi by M. because our d is 2 square root of p sine pi by m. So it is just the d min by 2 into n naught. So this is our bit error rate. This is a general formula. So we apply this. So here bit error rate is equal to q of d min is 2 root p sine pi by m. Here 2 by n naught. So bit error rate is equal to and it can happen in both the direction, this direction also and this direction also. So we'll multiply by 2. So 2 into q of a square root of p by n naught square sine of pi by m. So this will become, this is the final formula for our bit error rate of m array psk. For confusion, I will erase this. So with this we can solve, we can find the bit error rate of m array psk, m array quam, or qpsk, bpsk, and we have seen the how to find the bit error rate of all this uh, digital communication scheme through their constellation diagram. So today we will close the lecture here only, and this video will be recorded and this will be uploaded on YouTube. And in the next Tuesday we will solve the question based on the week 3, which is taught in the lecture of week 3. We will solve question based on that. So thank you everyone for attending today's class. If you have any doubt you can ask, else you can also ask in the comment section of YouTube. So we'll close the lecture here only now. So today we have studied bit error rate of BPSK, QPSK, M array PAM, M array QAM, and also at the end MPSK. So thank you. I will end the call for everyone. We will meet on Tuesday at 6 to 8.